Hey guys, so today's the day. Our efforts are finally going to pay off because in this very tutorial the window will be cleared. Let's begin. In the previous video we recorded the clear instruction into a command buffer and we said that this in itself doesn't really do anything because we have to submit the command buffer into a VulkanQueue in order for it to start executing. Remember that we usually have 2 or more images in our swap chain to enable double buffering, triple buffering, or even more. We created multiple command buffers, one for each image, to allow the GPU to work on multiple images concurrently. This means that in each iteration through the render loop, we have to submit a command buffer to a different image. You would expect this to work in a kind of a round-robin manner, simply iterating over the images every time. But things are not so simple. Depending on the pressure on the GPU, the next image available for rendering may sometimes be different than what we expect. This means that we have to explicitly ask Vulkan for the image to render in the current iteration of the render loop. This is called acquiring an image. This operation returns the index of an image which we can now render into. Once the image has been acquired, we can submit one or more command buffers which will execute on that image. At the end of the render loop, we have to tell the system that we want to present the image to the window. This of course can only happen after all the command buffers that target the current image have finished processing on the GPU. We can submit more commands into the queue while the GPU is taking command buffers out of the queue to work on. Minimizing CPU and GPU synchronization is critical for high performance. The application should be able to do the following: acquire an image for rendering, submit a command buffer, queue a present operation, acquire the next image, and continue uninterrupted. If the GPU is fast enough, there will always be an image available so that the application won't have to wait. If the application submits enough work quickly enough, the GPU will always be busy. This view is somewhat simplified, but this is the idea in a nutshell. Obviously, since we have multiple events that depend on each other running concurrently, we have to use some synchronization mechanism to create dependencies where they are needed. As always with Vulkan, we have to do it ourselves. Let's take a look at synchronization. I would say that the key point is the command submission. The function that submits the command buffer into a queue returns immediately so that the application can continue and the command buffer will start executing sometime in the future. Let's assume for simplicity that we rendered the entire frame in a single command buffer. Before the command buffer can start executing, it must guarantee that the presentation engine has finished reading from the corresponding image. This is somewhat confusing. The fact that we have just acquired the image doesn't mean that the presentation engine is done with it. Therefore, we must supply a synchronization mechanism that the command buffer will wait upon, which will indicate when the presentation engine is finished. This synchronization mechanism in Vulkan is called a semaphore. Now, semaphores are a bit out of scope for this tutorial. Computer science students typically encounter them in the operating system course, and I simply don't have enough time to fully cover this topic. Therefore, I'll just say in a nutshell that a semaphore provides 2 main operations: wait and signal. A process or a thread that needs to wait for a particular event or gain access to a synchronized resource calls wait on the semaphore. If the semaphore is in a signaled state, then the caller gains access and the semaphore becomes unsignaled. In other words, it is locked. A caller will hang while waiting on the semaphore until someone signals it. The use of semaphores in a VulkanQueue is somewhat unique. We don't signal or wait on the semaphore explicitly. Instead, we pass them on function calls and let the system do that when necessary. So the application is in charge of creating the semaphores that it needs, but the actual management of the semaphores, in terms of signaling and waiting, is in the hands of the system. When submitting a command buffer to a queue, we have the option to specify any combination of waiting and signaling semaphores. They are kind of like a pre- and post-execution semaphores, respectively. The command buffer will wait in the queue until all the pre-semaphores are signaled. Only then it can start executing. Once it is finished, it will trigger a signal of the post-semaphores. It is also possible not to provide a pre- or post-semaphores, or both. In the example today, we make use of a pre-semaphore, which indicates when the presentation engine has finished with the image. We also have a post-semaphore to indicate that the command buffer is finished executing. The present operation has to wait on the post-semaphore so that we don't present an image before the corresponding command buffer is finished. So when is the pre-semaphore signaled? We have to provide it when we acquire the image, and it will be signaled by the presentation engine as soon as it finishes reading from the image. If a command buffer is waiting for that image, it will start executing at this point. This shows you that we can acquire an image before it is actually available for rendering. Okay, so this is the theory. Now let's see how to implement it. Okay, so we are in tutorial number 10. Let's start on the application side. And most of the changes here are in the main render function. What we have here is basically the sequence that we saw in the background section. Okay, we have acquire next image. We submit the command buffer into the queue and we present the image. Now notice that the object that we are working with for all these function calls is something called MPQ, which is a pointer to a VulkanQueue class. This is a wrapper for the Vulkan API queue handle, which we're going to see in a minute. As you can see, it is declared here as a private attribute, a pointer to a VulkanQueue, and initialized to null. How do we get it? The VulkanQueue is initialized by the VulkanCore class. So after we initialize this guy, we can get the queue or the pointer to the queue from the VulkanCore. Okay, so we store it here and then we can use it in the render function. So the acquire next image function returns an image index, and we use that to submit the corresponding command buffer from the command buffer vector. Okay? And finally, the same index is used to present this image, again, using the queue. Okay, so this is the sequence. Now let's take a look at the VulkanQueue class. It is declared in this file. In order to initialize the VulkanQueue, we have to provide a logical device, the swap chain, the queue family index, and the index of the queue itself. Okay, so all of these parameters already exist in our VulkanCore, so there's no problem initializing the VulkanQueue. Next, we have acquire next image, which returns the image index. We have two submit functions that take a command buffer as a parameter. One is called sync and the other one is called async. We'll see the difference in a second. We also have the present function and wait idle. Wait idle simply means that we hang until the queue finishes all the command buffers inside it. Now for the private attributes, we have the logical device, the swap chain, the handle of the VulkanQueue. Okay, so this is the actual handle which is created by the Vulkan API. And finally, we have two semaphores. The first one is called render complete semaphore. So it is signaled when rendering to the image is completed. And present complete semaphore simply means that the presentation engine has finished reading from the image. Now let's see the implementation in QCPP. First, we have the init function with all of these parameters. So we save the device and the swap chain in the private attributes because we're going to need them later on. Next, we call a Vulkan API called VKGetDeviceQueue. So this function takes the device, the queue family, and the index of the queue, and it returns the handle of the queue. Okay, this is the VKQueue handle. Okay, so it looks like we don't really need to create the queue. It is already there. We just need to fetch its handle from the device. The semaphores are created in a different function, And to create the semaphores, I have a new wrapper function called createSemaphore. Remember the wrapper functions? We saw them in the previous video. Basically, any Vulkan API function which is a bit complex to call, I have a wrapper function for that in this file. So previously we had begin command buffer, now we have createSemaphore, which returns a handle of a semaphore, takes the device handle. Let's see that. The implementation is in wrapper CPP. Okay, to create a semaphore, we need to call a Vulkan API called VKCreateSemaphore, takes the device, the address of a create info structure, an allocator, which is always null for us at this stage of development, and we provide an address for the result. The create info structure has the usual type and next and flags. So this wrapper saves us the hassle of always filling up this structure. As you can see, we can use the defaults that we see here. As you can see, there is nothing special here. We check the result and we return the handle of the semaphore. Okay, back to QCPP. Wait idle is very simple. Just calls VKQ wait idle on the queue handle. Next, we have acquire next image. This function takes the handle of the device and the swap chain. This is why we needed them for the initialization of this class. Next, we have the timeout, which tells us how much time we are willing to wait until this function completes. So for example, if you want to wait no more than 10 milliseconds until this function returns, then you would put 10 million here, right? Which is 10 milliseconds in nanoseconds. And if no image is available within 10 milliseconds, then this function will simply return with some error that timeout has expired and there's no image. So right now we're not using the timeout, so we simply put the maximum value that you can put in an unsigned 64-bit integer. And then we're basically waiting forever, or almost forever. Next is the handle of a semaphore, which will be signaled when the image is actually available. We talked about that before. It's an optional parameter, okay, so you can put null here if you don't need this signal. Next we have a fence, a handle of a fence, which is also a kind of a synchronization mechanism in Vulkan. We're not using it here, so simply put null. And finally, we have the address of the index of the image, which is where we're going to get the result. So this index is returned back to the caller. Next, we have submit sync and submit async. And this one is more interesting, so let's take a look at that. In this function, we use the Vulkan API function VKQSubmit to submit command buffers into the queue. This function takes the handle of the queue, of course, and the number of submit info structures. So you can provide an array of this guy. In this case, we have just a single element in this array. So we have one here and the address of this structure. There is also an optional parameter here for a fence, but again, we're not using it at this stage. So what we have in the submit info structure? First, we have the waiting semaphores, which are the semaphores that we're going to wait upon, and only when all of them are signaled, we can continue with the execution of the command buffer. In our case, we have just one semaphore that we need to wait for, which is the present complete semaphore. Okay, this is the semaphore that we used in the acquire next image function right here. So when the presentation engine signals that it has finished reading or presenting the image, only then the next command buffer can continue. Next, we have the wait destination stage mask that basically tells the system where in the pipeline we want to wait. So this guy is an enum, and as you can see, it has many stages. You should be familiar with most of them, like the vertex input, vertex shader, tessellation geometry, all of them. And there are a few new ones here. In our case, we want to wait at the stage called color attachment output. Okay, we're not going to go too much into that. This is where we want to wait for clearing the window. After that comes the array of command buffers and the number of elements in that array. Okay, so we basically have two levels of multiplicity in terms of the command buffers with this function. So we can provide multiple submit info structures, and each structure can contain multiple command buffers. In our case, we have just one command buffer, so this is very simple. And finally, after the command buffers, we have the opposite of the waiting semaphores, right? We have the signaling semaphores. So these semaphores will be signaled after the execution of the command buffer. And for that, we have the render complete semaphore. So who needs to wait for the render complete semaphore? The answer is the presentation function. So this is a wrapper for the Vulkan API VKQ present KHR. And it's a bit interesting that this is a KHR function, because this may indicate that this function requires a kind of a getProc address for that, which I obviously haven't done. So it may be more correct to get the address of this function, same as we did with the other KHR functions, but at least it's working for me, so we can continue. Just remember that if you have problems here. So this function takes the handle of the queue and the address of present info structure. Here we have the waiting semaphores, same as queueSubmit, but in this case we will wait on these semaphores before the presentation engine can actually start presenting. Next we have an array of swap chains and the number of elements in this array. So this is interesting. We can actually present on several swap chains at the same time in the same function call. This is of course an advanced use case, so we don't need that. We have a single swap chain. And finally, we have the index of the image that we want to present. Now, since this function supports presenting on multiple swap chains, we need to provide an array of indices for the images, because we may have a different image for each swap chain. Okay, so this guy tells us the number of elements in the swap chain array and also in the image indices array. And again, because we have a single swap chain, we just need to provide the address of the image that we want to present. As I said, we also have a version of this function called submit sync. Okay, this is async, this is sync. This version simply takes no waiting semaphores and no signaling semaphores. We're not using that in this tutorial, but we will use it in the future. So that was the VulkanQueue class. Let's see where it fits into the system. Basically, we go back to the VulkanCore, which now includes this file. And we have the VulkanQueue object as a new member, a new private member in this class. So at the end of the init function of the VulkanCore, we call init on the queue. We already have the handle of the logical device, the handle of the swap chain, the queue family, and the index of the queue. We use 0 here because we just want to get the first queue in this queue family. So now that the queue has been initialized, our application code can get the address of the queue. This function simply returns the address of the queue. So in this tutorial, the queue is created by the VulkanCore, and it is used only in the application code. But in the future, we will see that the VulkanCore itself also uses the queue for various command buffers that it needs to submit. Now let's try to run this. And as you can see, we have a clear window set to red because this is the color that we set in the previous video. But unfortunately, we have quite a lot of errors in our terminal. So let's stop this for a second and take a look at these errors. So this error tells us that the command buffer is already in use and is not marked for simultaneous use. The Vulkan spec states that if any element of the command buffer's member of any element of submits was not recorded with the command buffer usage simultaneous use bit, it must not be in the pending state. So this one is easy to fix. Just take this bit and use it to begin the command buffer. Remember that when we record the command buffers, we have to begin and end the command buffer. And we use the wrapper function for that, which takes the usage flags in the second parameter. So instead of 0, let's place this bit here and try this again. And it seems like this error is now gone. Now, I'm not sure if this is an actual bug fix or a workaround. We may want to do something different in the future, but this will do for now. Now, the remaining errors are basically pairs of the same thing. As you can see, it tells us that images passed to present must be in layout present source or shared present, but they are currently in layout undefined. And the second error is practically the same. It tells us the command buffer expects image to be in layout general, instead it is in layout undefined. So using the Vulkan language, what this means is that we have to transition the layout of the image to one of these guys, either present source or shared present. And to do that, we need to use something which is called an image memory barrier, which is what we're going to do in the next video. So if you're interested specifically in image memory barriers or Vulkan in general, make sure to subscribe. Thank you for watching, and I will see you in the next tutorial.